Hello, everybody. My name is Thomas Lange. I'm a PhD student at the Technion. Today, I'm going to present a work of mine, which is joint with Professor Sefi Naor and Professor Gala Edgar. And our subject is offline and online algorithms for SSD management. So we begin with a few words on SSDs. We can think of an SSD as a table in which each column represents a block and each cell represents a slot. Logical pages to be written are of the same size as the physical pages. And to avoid confusion between these two from now on, instead of physical pages, I simply say slots. SSDs have limitations. They support only out-of-place page writes. Pages to be written should be written to a clean slots, and cleanings are performed in block granularity. Upon cleaning, valid pages stored in a clean block must be rewritten to another clean location. And the issue is that such page rewrites are bad because they reduce the endurance of the SSD and harm its performance. The contribution of this research is threefold. First, we formally define the SSD management problem. We address this problem from a theoretical perspective. In particular, we analyze algorithms in a worst-case fashion. Finally, we propose an efficient approach for reducing write amplification in SSDs, and this approach can be applied in both offline and online settings. Okay, so we now present our model. We assume that if every time t a new write request arrives, the requested page should be written to a clean slot. The previous version of that page becomes invalid. And upon cleaning, every valid page in the clean block must be rewritten to another clean slot. And our goal is to minimize write amplification. Let's take a look at the figure below. Green cells represent valid slots, dotted cells represent invalid slots, and white cells represent clean slots. And assume that we want to write a page to this SSD. So we should write it to one of the clean slots, let's say here, and the previous version of this page becomes invalid, for example, this one. And assume now that we want to clean a block. So, for example, we can clean this block, the red one. However, note that a valid page is stored in this block, so it must be rewritten to another clean location prior to cleaning. So it is moved here, and now we can clean this block. When we think of algorithms for SSD management, we distinguish between two components. The victim selection determines which block to clean when, and the placement strategy determines where to write each page. Two classical algorithms are greedy and hot code. The greedy algorithm always selects the mean valid block for cleaning. And regarding the placement strategy, it simply fills that block. Actually, it does not distinguish between different pages. Hot code is actually a family of algorithms that allocates different blocks for different page temperatures. And all of them apply greedy cleaning within each area. Okay. Regarding the performance of these algorithms, so it was shown that the greedy algorithm is optimal under a uniform distribution. And however, hot code seems to perform better when the distribution is skewed, which commonly happen in realistic traces. In the first part of our work, we concern myopic algorithms, where a myopic algorithm is an algorithm that has no information about the future. We express our results using the spare factor, denoted by alpha, which is defined by the difference between physical and logical capacity over the physical capacity. And we have here three basic results. The first one states that for any request sequence, the right amplification of the greedy algorithm is not greater than 1 over alpha. The second result states that no deterministic algorithm can provide a better guarantee. That is, for any deterministic algorithm, we always can find a request sequence on which the right amplification of that algorithm is at least 1 over alpha. And the third result is that no randomized algorithm can provide guarantee better than 1 over 2 alpha. Okay, so now we turn to describe our approach. A key notion here is the death time. The death time of a page is simply the time it will be accessed next. So ideally, it was shown that each block should group pages with consecutive death times. This way, blocks are invalidated sequentially and no rewrites needed. Unfortunately, when the sequence is not sequential, we mostly cannot maintain such an optimal layout. So our approach is like this. We start with an optimal layout. We serve new requests while keeping the layout almost optimal. And when the layout becomes too far from being optimal, we reorder all pages. Okay, so now we turn to describe how we apply our technique in the offline setting. So we begin with the victim selection. So we clean blocks in general only when the SSD becomes full. That is, it does not contain any clean slots. So in this case, there are two options. If completely invalid blocks exist, that is, blocks that contain only invalid slots, then we clean all of them, okay? For example, here there are two completely invalid blocks, we clean both of them. Otherwise, if such blocks do not exist, then we reorder all pages, and we reorder them by the death times. For example, if this is the initial state, there is no block that is completely invalid, then we reorder all the pages such that each block groups pages with consecutive death times. Okay, what about the placement strategy? So after a cleaning step, we have a set of blocks which are all clean. That is, all their slots are clean. So in this case, we consider the next requests, in particular the death times of the next access pages, and we write the pages into the slots such that they are sorted by their death times. For example, if we have two clean blocks, 4 slots each, so we consider the next 8 access pages and we write them in a sorted manner in the clean slots. Regarding the performance of this algorithm, so we can show that for any request sequence, the right amplification is not greater than 1 plus O of 1 over B, where B is the number of blocks in the SSD. This is a very efficient algorithm. And the key idea in the analysis is that the reordering steps are very rare. And note that this is the only place in which we perform page rewrites. A natural question is whether our algorithm is optimal. Consider for a moment the following decision problem. We have a request sequence sigma as an input, and we ask whether sigma can be served without rewrites. That is, with right amplification, which is equal to 1. It turns out that this decision problem is a special case of a graph problem named fragmented coloring on interval graphs, which is a generalization of standard vertex coloring. However, the computational status of this problem is open. So for now, we cannot determine whether our problem is NP-hard or not, and we leave this question open for now. We now turn to augment the online setting. such that we assume that each request arrives with a predicted death time. Our goal in the placement strategy is to sort pages by predicted death times. However, we tackle a problem here. Look at the figure below. Assume that we have two blocks, which we fill with next access pages. And we already filled 6 pages with death times 1, 2, 3, 7, 8, and 9. And now a page with predicted death time 5 arrives. So actually, we do not know where to place it, since this decision depends on future requests. So we propose the following solution. We assume the availability of a small, fast additional memory. And when I say fast, I mean that we allow ourselves to neglect any implication concerning its management. So we use this memory as follows. Instead of writing pages to the SSD immediately, we first aggregate them in the memory. And as soon as the memory becomes full, we move the pages to the SSD, sorted by the predicted death times. Note that in practice, predictions might be erroneous. So we define the prediction error denoted by eta as the sum over all requests of the difference between real death time and the predicted death time. And note that in our placement strategy, we just believe predictions. The question is, what about the victim selection? In the victim selection strategy, we have two options. The first option is to consider predictions. For example, we can avoid cleaning a hot block. However, the problem is that in this case, large prediction errors can be disastrous. So in order to limit the effect of prediction errors, we choose the following option, in which we always clean mean valid blocks regardless of predictions. Okay, so now we turn to illustrate the operation of the proposed algorithm. We assume that initially the memory is empty and the SSD contains no clean slots. So in this case, the first step should be a cleaning operation. And we select mean valid blocks whose capacity is equal to that of the entire memory. So in this example, we select 2 mean valid blocks for cleaning. The mean valid blocks here are these blocks. So we choose them for cleaning. They store a valid page. So we retrieve this page back to the memory. Okay, now we turn to clean the victim blocks. And the next step is to serve the next requests until the memory becomes full. So let's serve the first request. The first page is written here. The corresponding slot becomes invalid. And this way, we continue until the memory becomes full. At this point, we write the pages stored in the memory to the SSD, and we do it such that the pages are sorted by their death times. Regarding the performance of this algorithm, we proved that for any request sequence, the right amplification of this algorithm, which is now given as a function of eta, is not greater than the minimum between 1 plus O of eta over t, which is the average prediction error, and 1 over alpha, which I remind you is exactly the right amplification guaranteed by the greedy algorithm, plus a negligible additive factor, which depends on the memory size. So our algorithm actually possesses 2 desired properties. First, its performance improves as the error decreases. And second, it is never worse than the greedy algorithm, which knows nothing about the future. So before we show the empirical evaluation of our algorithms, we present a simple optimization we implemented for the simulations, in which we simply use the memory also as a cache. Since cache writes are for free, if a requested page if the previous version of a requested page is already in the memory, so we can simply overwrite it. So in this case, due to cache hits, note that write amplification may be smaller than 1. Okay, so experimental evaluation. So in the first experiment, we compare all 4 algorithms, greedy, hot, cold, online, and offline. All algorithms are equipped with a memory of size 1% of the entire SSD. Greedy and hot cold use memory as a cache with LAU policy. And in this simulation, predictions are exact, okay? And hot cold uses the predictions to determine the temperature of each page. We consider 2 traces here. One was taken from a uniform distribution and one was taken from a ZIF distribution. On the left, we can see the uniform distribution. We can see that both offline and online algorithms achieve write amplification, which is very close to 1. In contrast, hot, cold, and greedy achieve much higher write amplification, which gets better and better as the spare factor increases, obviously. However, there is a significant gap between our algorithms and greedy and hot cold. In ZIF, the gap decreases. However, there is still an improvement. We can see here. And obviously, all algorithms perform, the performance of all algorithms is better in the ZIF case, mostly because the memory is very, very efficient as a cache in this case. In the next experiment, we use both exact and erroneous predictions. Predicted death times are distributed uniformly in the interval T and Y of T, which is the real death time. Spare factor is fixed here, and various memory sizes. Note that the dotted bars represent erroneous traces. You can see that the online algorithm still outperforms hot cold even when prediction errors occur. However, the gap is much smaller now. You can find further details on the experiments, including real traces, in our full version paper. So conclusion, we present here a theoretical analysis of both existing and new algorithms. In particular, we presented the new algorithms that group pages by death times. We saw an offline algorithm and an online algorithm, and we believe that these algorithms can lay the ground for the development of a new class of practically applicable algorithms that the systems community has not yet considered. And we actually start bridging the gap between the systems community and the theory community. And we hope that our findings may motivate the theory community to address SSD-related design challenges, which have been overlooked so far. That's it. Thank you for your attention. I'm here for any question. That's it. Bye-bye.